Okay, so hello everyone. This is Muhannad, Ahmed, Abdul-Ati, Kenzi, Islam, and Adham. And we are going to present jaw surgery prediction using deep learning applied to X-rays in the general population. It might seem like a complex name, but I'm going to break it down. So first, you might have seen people with problems with their jaws. They might have problems with their lower jaws, as seen here, or upper jaws, as seen here, and the misdiagnosis of such a case leads to severe complications. This famous case of an American football player, they misdiagnosed him and the dentist told him that he does not need a surgical intervention. But then afterwards, it turned out that this person needs a surgical intervention and it leads to painful and complex complications after this. We have 4 intervention cases. First thing is surgery on one jaw. Second thing is surgery on 2 jaws. Third thing is that this person only needs braces. And the fourth thing is a healthy patient. And the challenges that we are trying to address are 3. The first thing is the time-consuming process for the dentists. The second thing is the subjectivity. Dentists might not agree on the diagnosis of the case. Third thing is the diversibility. The shape of the jaw itself might differ from one ethnicity to another. And here comes our upper-level design. The dentist only needs an X-ray of the patient, and then we are going to provide a diagnosis for the patient. And this is going to happen through our solution, OrthoNile. You only need to provide the X-ray, and you're going to... You only need to provide the X-ray, and you're going to have the diagnosis. But before introducing our solution, we need to understand the dentist's journey. The dentist starts by exploring and inspecting the X-ray. Then they start by annotating the landmarks on the skull. Then from the landmarks, they calculate some angles, and using those angles, they diagnose the case. So we are introducing... Sorry, I don't know what is happening with the... Okay. I'm not clicking. And moving to our pipeline, our main pipeline is that we provide the input, and then we have pre-processing to enhance the quality of the image. Then we take the landmarks and pass it to the data augmentation to increase the number of the pictures that we have. And then we generate the heat maps. And after generating the heat maps, we train the model on the heat maps so it can generalize and then provide the heat maps for us. And from those heat maps, we can then calculate the angles that we are going to use for the diagnosis. Next slide. So how are we going to automate the process of the dentist? So the first part of annotating the landmarks, we're going to replace it by the image annotation module. And then we are going to replace the angles calculation by our script for calculating the angles. And then for the diagnosis, we're going to replace it with our classification module. And then the whole process has been automated. We have a new add-on based on consulting Dr. Mustafa Dawalatli, and he told us that it's very important for the dentists to see the soft tissue segmentation. So we added this as an extra work on our thesis. And then we have added a chatbot as well. And this chatbot is going to help the dentists in the diagnosis for asking questions about the case. And all of this is going to be combined in our solution and the GUI OrthoNile. And now we have just the time and the subjectivity problems, but we still have the diversibility problem. How did we solve the diversibility problem? Through our diverse data set. We have 1,000 images from Pakistan. We have 400 images from Taiwan. And we have 205 images collected for us by Dr. Mustafa, Dr. Noura, and Dr. Muhammad. And we have 158 images from United States of America collected for us by Dr. Tariq. So now we have a diverse data set. So we have solved the problem of diversibility. And this is our full pipeline. And we're going to start with the first step, which is the pre-processing. We need to enhance the quality of the pictures. So we applied 2 main techniques, Clahi and denoising, to remove the noise and enhance the contrast of the pictures. And as you can see here, this is before applying the pre-processing. This is after applying the pre-processing. And now we are going to move to the next step, which is the data augmentation that's going to be presented by Islam.
Moving on to the second step in the pre-processing, we have to first collect and annotate the landmarks. Basically, to reiterate, our goal is to do geosurgery prediction, and the first step has to be the annotation of the landmarks. And these landmarks are our points of interest. Basically, our landmarks are the anatomical reference points that you can see here that the orthodontists and dentists in general use to assess the facial structure or do the geosurgery prediction. And since our goal is only to do the geosurgery prediction, we only selected 19 points across all the data sets. And mainly, these points include the SELA A and B points. Next. And even the data set that Muhannad have mentioned wouldn't be enough for the deep learning model that we are going to present. And that's why we have to do a couple of data augmentation techniques that include zooming, rotation, and intensity enhancement so that the distribution of the image is greater and the number of images are doubled by 2. And one last step before presenting our model is the heat map generation. Again, we are relying on deep learning, so it would be very difficult to optimize and regress the landmarks directly from the X-ray image into exact X and Y coordinates. That's why we gave deep learning what it likes most, which is probability, and we generated from the landmarks heat maps using Gaussian distribution. And finally, we are ready to present our first model, which is the image annotation or landmark annotation model. It's called CEF-RES MHNet, CEF for cephalometric, which is the study of the X-ray, the study of the head and soft tissue on the X-ray. RES, which is residual convolution blocks, MH, multi-head decoder, and net network. So it's basically an encoder-decoder block with one encoder and 3 decoders, and the input is just the pre-processed cephalograms, and the output is 19 images or channels, each one with a heat map representing a landmark. Let's get into detail into the architecture. As you can see here, we have first the encoder. Its mission basically is to learn low-level features such as lines and edges, and high-level features such as deciding if a batch of the image is the jaw or not. And the decoder is where this gets more interesting, since unlike most models in the literature, we are employing 3 decoders. Each one is specialized in a set of heat maps or landmarks. So the first one, 7 heat maps, second 6 heat maps, and so on. And the intuition being is that instead of upsampling all the features, we are trying to upsample only the distributing the work among them. And finally, at the bottleneck, we have the dual attention module, the spatial and the channel attention to attend to the relevant pixels in the image and attend to the relevant features in the image. And that's all technical, so we have to do the experimentation and results with Jaheen.
And now we need a reason for everything that we did in our architecture. The first experiment for the ablation study is with the multi-head decoder, but without a resonance. It's a convolution, and the result was really good, but it wasn't the result that we wanted. As we can see here in the chain, there is a missing point. So we tried also with resonance, but without the multi-head decoder, as we can see here. And the result really enhanced, but we still need more and accuracy, as you can see here in the chain. So we tried our last experiment, which is the full architecture that Islam just explained. And as you can see here, the chain detected almost all the points. And these are the results for each of our ablation studies. We got the highest accuracy with the full model. And this next our CEF-RES results comparing to all of the other results. We get a success detection rate and the lowest MRE. MRE is basically the difference between the predicted and the ground over the average, all of the points, and using only less than 75% of the parameters. And this is our reference for our paper. And next was the pipeline. After we get all the landmarks from the last module, we calculate all the angles for the second module, which is the classification. As you can see here, these are the important angles that we are comparing, which is SELA-Nasion A angle and the other, SMB and AMB. And this is for the vertical angles, which is the y-axis, the gonial, and the SELA-Nasion mandibular plane. And next in the pipeline is the classification. The classification starts with manual labeling by Dr. Mustafa Dawalatli and his team, Dr. Muhammad and Dr. Noura from Las Laini. And then we did the landmark, we used the landmark coordinates. And after that, we did the feature engineering to calculate all the angles after the JSON file, as we can see here for the angles that we just said. And after that, we did a normalization scaling using the score normalization. And we checked according to the dentistry, the normal range is from 80 to 84, for example, for one of the angles, SNA. And after that, we did data cleaning and validation. We removed all the outliers and confirming that the coordinates are the ones that's extracted. And lastly, we did a train test split with 80% to 20% train versus testing. And the last step is we tried various methods such as random forest XGBoost, which we're gonna talk about later. And finally, our output is one of the 8 known classifications, diagnosis classifications from the dentistry. And next was Abdulati for the classification results.
So the results of the whole pipeline, where the training was mainly done on the Pakistan dataset. As Jane has mentioned, we trained a bunch of models. Most of them are decision-based, random forest XGBoost, gradient boosting, decision tree, and logistic regression. The best model that was able to perform was the random forest with a precision and recall of around 84%. As you can see, the logistic regression did not perform very well, which further validates the decision-based mechanism of the whole training. No. Okay, we have already mentioned this one. Okay, I think هو الترتيب فين؟ ممكن تقلب؟ Okay. Next with the confusion matrix of the training. As you can see, the confusion matrix looks almost perfect. We have some confusions in the both and the lower. As you can see, there are 12 confusions. But even the model was confusing both classification, both classes. It's still detecting the subclasses correctly, which is the mandibular advancement. The same happens for the 9 confusions. And to further validate our whole training process, we use the dataset obtained from Egypt as a test dataset, mainly as a test dataset. And we can see our best model was performing really good, 89% precision, 86% recall. And to further validate the whole decision-based tree training, we analyzed the feature importance. And as you can see, the top 3 features that were biasing the whole decision process was the AMB, SMB, and SNA angles, which are validated in clinics by orthodontists to be the top 3 features that are biasing the decision. And next, Kenzie will introduce the third model, the soft tissue segmentation.
Okay, how do you move forward? Okay, so we're gonna discuss the segmentation of the soft tissues, which was an important feature after consulting the dentist. So we first tried SAM2, which is Meta's segment anything model. While it can produce, like it had the possibility to produce high quality segmentation, it was faulty because it has 2 modes. You either place dots or you place a box, but because we can generalize it to all the data set, we opted not to use it. Oh. Okay. As you can see, it's hard to generalize, like the same points we used in the last slide did not work on the other one. So we thought we would use grounded SAM, which is the version that came after SAM2, but also we were not able to generalize. So we moved on to UNET, and Abdulati will discuss that.
So our solution was basically to customize our own model for segmenting the tissue to tackle the challenge of generalizing the model over the dataset. We manually annotated 95 X-ray images by tracing them manually, as you can see in the GIF, and we trained the unit architecture over it, and we were able to obtain a score of intersection over union with 98%, and with a lower number of parameters than our competitor with almost 500,000 parameters. As you can see, our competitors SAM2, grounded SAM, and mid-SAM have a huge number of parameters with 200, 600, and 93 million, while our own customized model was only 500,000, and these are the references. And next, Kenzie will introduce again the module 4, the chatbot.
Okay, so we thought to add a module, which is the chatbot, to help the dentist explain diagnosis and access research paper faster. So we had a chatbot with retrieval augmented generation. It's backed with a knowledge base of over 1,300 research papers, and it provides real-time explanations with citations. So the pipeline goes, the user sends a prompt, and then we use a vector transformer to transform that prompt, and then we do vector search in our database using cosine similarity. And then we inject the context with the research that came back as relevant, and we send it to the LLM, which is Llama 3.1. And then it generates the answer and sends it back to the user, all in 2 to 3 seconds. So our dental knowledge base, we used PubMed by using 75 keywords to extract relevant research. And in total, it was 15 megabytes. And then the embedding model we used was ManyLM, and it outputs a 384 dimensional vector. We used for vector similarity, we used cosine similarity, because it's magnitude independent, and we did not want the length of the research to affect the decision. So it captures the semantic meaning, not just the keywords. And for the model, we used Llama 3.1, and it's hosted on Grok API. Okay. So now, okay, no. Hellos. We're moving on to the GUI with Adam.
All we have seen so far is the back end of our application. That's what we can see as students. But the next part is what everyone can see as a user. So the GUI, our main application, is mainly divided into 2 main panels. We're going to start with the left panel. So the left panel has 2 main tabs, as we can see. The first one is for the segmentation model that we explained. So basically segments the soft tissue. So as we can see, all the user needs to do as a dentist is just upload an X-ray image, and it takes a couple of seconds, maybe 5 seconds, and then you will have the soft tissue only segmented. So there's a mask, and there's also an overlay on the skull, so you can see the whole skin. And you can also save it later on your device. And then the second panel is for the landmark detection. So it's for the second AI module. In this one, you still, again, need to just upload one image. Usually they work in parallel, but for the sake of the video, I'm uploading it again. So once you upload an X-ray image, it takes a few seconds, and then you have the image annotated. But that's not only what you have. You can also start by removing specific points in case you just want to show a very specific set of landmarks. So you can just hide all of them and start showing only the points that you want. And you can also just hide them and show them again. And you can adjust the size of each landmark based on whatever you want. And not only that, because as a dentist, we know that this is AI, it's not perfect. So you can adjust the landmarks. And if any mistakes happened while adjusting the landmarks, you can always go back to the first predictions made by the AI. And then you can also at the end save that locally on your device. So yeah, so you just save it, you can save the as an Excel, and you can also save them like the image annotated itself. And then after that, we're gonna move to the right side, which is like the next part, the right panel. It also has 2 main tabs for 2 different AIs, as we said. The first one is for diagnosis. This one gives us the decision. So what is the outcome of the whole diagnosis. So it basically calculates some angles based on the landmarks that we already annotated, and then gives you the final decision. But it also tells you the probabilities of each decision. Like the AI thought that it would be 72% this decision, and it shows you all the 8 classifications and the probabilities of each one. And the last tab that we have is our AI assistant, as Kinsey talked about. It's supported by more than 1,300 articles, dentistry articles. And you can ask it basically any question. Here I'm asking a question that's very complicated for me to know, and just gives you all the answers based on the 1,300 articles, but also shows you the references, so where he got this information from. And at the end, of course, you can just clear the chat. So basically, this is our AI, this is our application, and that's how dentists are going to be using it. Now we're going to be discussing the business model with Abdelat.
And now for our business model for the whole commercialized product, it's three main categories. The product value, we offer time reduction in the whole process, clarity through the soft tissue segmentation, AI assistant through the chatbot we offered. For the cost structure, it's mainly split over the R&D expenses, the sales, personal cost, the customer support, and of course the cloud infrastructure, hosting over AWS or GCP. Our revenue will basically depend on software as a service, as we see through our product, for the API access for third parties. Now for our market and stakeholders, we'll be mainly targeting dental academics, researchers, surgeons, dentists, clinics as our customer segments. For the key partners, they will mainly be academic researchers, dental profession association, AWS, as we are hosting there anyways, the imaging centers. For the key resources, for the technical ones, it's mainly the AI models that we are implemented. For the human ones, it's basically the engineers and the orthodontists. Then these are the human resources involved in our application. For the operation channels, we have live demos, as we are doing it right now. For the association partnership, we have already applied to ISBI as well, sales team, and referral programs. And our key activities will be mainly focused on the model continuous training, software continuous maintenance, the development of the software, Q&A, and data collection to ensure continuous maintenance of the model. Our customer relationships will mainly focus on the technical support, online forum, and product update through a continuous feedback loop system for continuous improvement. And now Jaheen will discuss the competitor analysis.
So now, after doing our research, we found that we have a lot of competitors all over the world. And to do our the X and Y coordinates, we found that after doing a ground research with dentistry students in Egypt, we found that they really care about how much money they're gonna pay and what's the accuracy that the higher the accuracy, the higher they want. So we found that in Egypt, it's only WebSafe and Dolphin Imaging is the only two that's using by dentistries and clinics in Egypt. So we found that this is our competitors. Next. So we have WebSafe and Dolphin Imaging. OrthoNile, that's our product for now. It's affordable and unified, and not only this, but it's powerful also at a very low cost. And next was Mohannad for the recommendations.
Okay, so for the recommendations, we recommend that the people that are going to work in the future, they can introduce a model for the correction. You can pass it the X-ray, and they can show you the X-ray after the treatment. The second thing that we are introducing is to introduce an LLM to suggest treatment plans. The third thing that we are the recommendation that we are introducing is increase the number of the landmarks detected by the model itself. And then for the thesis takeaways, we have we have reviewed and analyzed more than 35 peer-reviewed papers, and we have conducted 50 plus training experiments, and we have experimented with 20 plus deep learning and machine learning models. And last but not least, we have submitted our research paper to IEEE ISBI conference, and we're waiting for the results. And for the empowerment outcomes, we have submitted our research paper, and now we have the product. Thank you so much.